just tell me if it's positive or negative in terms of the value. So if you need extra practice on that, I know it's not an easy topic to kind of get down, but it seems like you all got it. Thank you. I'll hit the lights now. Hey, before we go into 14.4, because then we've done it all, we've done partial derivatives from tables, 3D graphs, contour curves. We should come back and do a couple more equations. All right, so try this one. Here's a function of x and y. Well, I can put a t. X to the fourth t squared cosine we'll put a 2 there. 2y plus t plus 5y. And I need you to find this. Find the second partial derivative. But I have it in another notation. So let's talk about that notation. This is what we're going to find for that function of x and y and a variable t. So this looks weird, don't it? See this notation? This is a second partial derivative. But is this fxy or is it fyx? Which one is it? It looks like xy, doesn't it? It looks like fxy. Well, look carefully. You know what this really means? This means take this derivative here, and then take the derivative of this with respect to x. So it means do this first, then this. So believe it or not, this really means this. I'll let you put that in your notes. So if you ever see this notation, you can just say to yourself, okay, I can read the denominator from right to left. This means do the first partial with respect to y, and then take the second partial with respect to x. Do the first partial of the function with respect to y, and then do the second partial with respect to x. Hey, but do you remember Clairaut's rule? What is fxy equal to? fyx, remember that? So what if I did it backwards? I'll still get it right, won't I? Cool, because of that rule. So have no stress there. But I do want to point out, this means this. So if this was like a third derivative and it wrote xyz, then I would have gone zyx. Okay? I know that notation looks funny. Okay, so if it means this, then let's find this first. What is the first partial with respect to y? Well, that's easy. What will that become?
5.
That's 5. I'll get this right here. Do y'all agree? We're doing partial derivatives with respect to y. So x and the t's are all constants. So they stay, don't we? What's this cosine become?
Negative sign.
Negative sign. Now what about the 2y? We got to apply a chain rule. That's just a constant. So we get negative 2. Everything else stays the same. That becomes sine. 2y plus t, and then I'll put the plus 5. Boom, good job. Was that what we got this? I kept the x constant, I kept the y constant, everything else is held constant except for the y. I differentiate only with respect to y. Now we need fyx. Sometimes this gets people on the test. What's that become?
It stays the same, right? We don't do anything.
Does it? Then what do you
Constant.
mean?
0.
0. Do you agree?
Mm-hmm.
Does everyone agree this will turn into 0? Take the derivative of this whole expression right here with respect to the letter x.
Okay, yeah.
Right? And you're like, well, it's a 5. Oh, hey, how about this? What if this said 5y squared here? I'd still put a 1.
Yeah.
0. It doesn't have an x in it, right? It's a constant. So let's say this said 5t cubed y cubed. 0. So good. Hey, so what happens here? This stays constant. That stays constant. But what happens to this x to the fourth? Because you do have to differentiate that, right? You get negative 8x cubed. And look, just don't change this to cosine. It stays what? Sine the 2y plus the t. plus 0. And you do not have to put the plus 0. Is that okay with that? Right. That's the only, be careful of that stuff. Be careful of those little things. Like this. Here's another one. G of x, y, t. 5x squared. Y minus y cubed plus t. And then when you're going to find g of y at the value 1, 1, 1. So we got to find the partial of g with respect to y and then plug in the numbers 1, 1, 1. Don't let this get you. What is g sub y there? The first partial of g with respect to y. What's this become?
5x squared.
Just 5x squared. Brilliant. That's easy. Here's the thing we're talking about. What does that become? What happens to plus t? Yeah, plus 0. Nothing. Right? Take the derivative of that respected. That's what I mean. Sometimes people accidentally let that t hang around. They're like, wait, I thought we keep the t. It's like, you're taking derivative of that t, which is a constant with respect to letter y. There you go. Just plug in 1, 1, 1. What's 5 minus 3? 2. Oh, no, the good thing about the equations, we only did a few equations, but this is just going to keep coming up in section 14.4 and 14.5, so we don't have to spend like an half an hour where I'm like, give you another equation, give you another one. Plus I put a lot of practice problems. If you want practice for like logarithms, you know, doing partial derivatives with logarithms, they're all in there. Cool. I mean, but these are going to come up throughout the problems that we work, so we'll get the practice then. We'll get a lot of practice with partial derivatives from equations. Everyone's okay with that? Excellent. Excellent, excellent. All right. So now, we're going to put down section 14.4. I'll raise this. Tangent planes. Haven't we already found an equation of a plane? So now we're talking about planes that are pretty tangent to the three-dimensional curves. Get this.
Graph? No graph.
Oh,
That's
no.
all.
We're good.
Gotcha.
Well, maybe there's like a sphere here, and there's some point. But we can get the equation of a tangent plane to a surface. So remember, a tangent line to a curve, tangent plane to a surface. We just need the equation. Well, it may look familiar. Do you recall this? When I'm going to draw a curve and draw a tangent line. And that's the point, right? You know, Calc 1. Do you know his equation on a tangent line? It was y minus y sub 1. I'm putting it in point slope form. Equals m times x minus x1. You're going to laugh because the equation of a tangent plane looks just like this. It's going to look like this extended. So isn't that true? And this m, wasn't it the first derivative of x? Something like that here. I was like, well, you were f prime of x. Okay, y minus y1 equals f prime of x. The equation of a tangent plane is, at some point, and let's use the point, how about x naught, y naught, z naught. That'll be our point. And the equation of a tangent plane will be, it's going to look just like this, z minus z naught equals, okay, I need this. But I need one for the x's and the y's now. Use partial derivative. Fx at the point, x minus x naught, plus fy at the point, the partial derivative with respect to y, y minus y naught. Okay, a lot of times if you find it easier, I can write this bigger. you might just say, this is really fx. And you might think this is just fy. I didn't want this to bug you, this notation here. I'll get out of the way because then you're always copying. But this just means evaluate at the point, the slope evaluate at the point. Slope of f in the direction of the positive x-axis. That was the slope of f in the direction of the positive y-axis, right? But sometimes, I just want to, this is going to be a numerical value we all find. It's going to be a slope. This right here will also be a numerical value we're going to find. Just like you always did with here. The slope was 3. This might be a 3. That might be negative 2. The slope might be 0. But then it looked just like this. Cool. So let's try one. Heck, I need to give you an equation. How about, I want to use some surface that we're very familiar with. How about the paraboloid? So when I want a paraboloid, it's like a windsock, right? Now let's say the paraboloid is, in fact, I think I'll invert it. The windsock will go like this. Some kind of windsock, let's say 2 minus x squared minus y squared. So that would be some windsock that was like, like this, went up 2 notches on the z-axis, right? And then it just opens up like that. Now I gotta pick a point. How about when x is 2 and y is 2? And when I have to pick some point, how about I'm gonna use when x is 2 and y is 2. The only thing is I don't know the z value. What would be the z value there? Because I just made this up. And we'll find the equation of the tangent plane to this surface, which is a paraboloid at this point. How can I get the z value? Just what?
Subtract them.
Yeah, let me substitute. What's 2 minus 4 minus 4? Negative what?
Negative 6.
Negative 6. So when it's almost like, oh, see this wind? Here's this. Here's this too. Got this paraboloid going on. Like a windsock, right? But we're using a point x equals 2, y equals 2, but then it was down at negative 6. And we're just going to get, what's the equation of the tangent plane right at that point? The equation of the tangent plane to the surface, let me write the surface down, because I want to make sure when you're copying this, you know what I'm talking about. I got a lot of writing on the board. The surface was z equals 2 minus x squared minus y squared. And the equation of the tangent plane to that surface, at which point? At the point given as 2 to negative 6 is, and I'm just going to write all that down, z minus z naught equals fx, x minus plus fy. And we just plug in all the points. What's that number? Negative 6. What's this number? 2, and what's this number? 2. But these are partial derivatives, aren't they? So now you gotta look at that surface and find the partial derivative of f with respect to x, then plug in the value. Or plug in the values. You'll see one like this is like number 7 on the practice set. All right, well, what's fx? I mean, what's the, there's f. That's the function of x and y right there. What's the derivative of this with respect to x? 0 minus 2x minus 0? Don't get negative 2x? So this is huge. Do not leave the answer like that with a negative 2x here. I know I'm writing it like this, but we really have to substitute a what? The point. You're getting the slope, it's at some point on that surface. And you do got to plug in the point into the slope. So what's partial of f with respect to x evaluated at the point 2 to negative 6? What's going on here? I'll just write down at x equal to a 2. What do you get?
4, negative 4.
So you will always get a value right there. Always. Don't leave it with like variables and stuff. Negative 4, 12, 6, 2, 0. It won't be negative 2x or something. And how about this guy? What's with respect to y? I can name 2y. Now you gotta plug in y equals 2. You get the same number? There you go. You can leave the answer like this. But I'll write it in another way too. By the way, the negative negative becomes a what? Is that what I got? So see how I got these slopes? Partial derivatives, substitute the value. Or what's another way to write this? Negative 4x plus 8 minus 4y plus 8 minus z minus 6 all equal to a 0. I wanted to show you this is just like the planes we were doing back in chapter 12. Section 12.5 we learned about equations of planes. This looks just like it. Negative 4x minus 4y minus z equals negative 6? Is that right? That'd be 6, no, not negative 6, negative 10. I'm gonna double check it. Negative 8 minus 8. All you gotta do is plug this back in there, right? Negative 8 minus 8, negative 16. Negative 16 plus a 6, negative 10. Or what's another way to write that? Or I can do what? 4x plus 4y plus z equals what?
Negative 10.
Now positive 10, right? If I
Oh,
multiply
positive,
negative
yeah.
on both sides. These are different ways to write this answer. This was fine too. You absolutely can leave it like this. But if it's one of those multiple choice problems, manipulate it to see how they wrote it each way. And why did I do this? What are these numbers here again? The 4 and the 4 and the 1. We don't care about the 10. The 4, 4, and 1.
The normal.
That's the normal vector to the plane. That's that vector what? Come right off that plane.